this. Today I'm going to talk about how to convert coupling phi using Redfield tensor methods. So actually those methods um, explain how electronic state propagation of electronic state. So I used my model is I used a polycitylene model, and that one for single oligomer. And here we did the coupling and things, and I didn't add how to do the coupling because already Ami explained those things 2 weeks ago. So I have around more than 500 more than 500 coupling files. So what we need for calculate and plotting those graphs, we need a coupling files, energy pop file, and obviously the Matlab code. And here the energy profile, actually this one shows the energy of state. Like if suppose we have we want to calculate, we have HOMO and LUMO, we want to calculate uh, 40 HOMO and 40 plus HOMO. It's a orbital before HOMO, and after LUMO 40, then we will able to get to know the energy of state from the energy profile. So we need, that's why we need energy profile. If anyone confused of the energy profile, they can look at the input overlay file, and that will be helpful for our calculation. So this correlation Matlab code obviously provided by professor, and oh, sorry, yeah, need to go. Yes. So here, this one actually HOMO for my model, and this one is like maximum state of that model, and this sorry, this one maximum state 99, and this one minimum state of that model. So I all here um, oh, here we need to load the energy profile, and obviously when you will calculate it, need to plot this one, you need to download all coupling file in your local directory, and obviously you need to save the Matlab code in the same directory. So then you will able to run the Matlab code. And here the most important things is the one I showed in red box, this one. And obviously you need to modify this, like for each model, or if you want to plot, like suppose I mean plot from 1 to 100, like that. So you need to change the number of coupling files according to your model, and the number of uh, steps to take. So it shows the uh, how many times required, and from this method, what happened? Just 1 minute. Yeah. So that's the Matlab code, and I already said that we need in all coupling files, energy profile, and obviously the Matlab code. And when you run the code, you will able to get yeah, several graphs. And this one here um, the yellow one, it's like tall, like a building shape, like let's say like a column, tall column, and a small column. So the higher the column means it shows the relaxation, how quickly the state actually relax. relaxation of the state. So the higher the stick, that means it quickly relax the system. Lower the stick, that means the relaxation time is small. And there I think relaxation time is more. That's why there is nothing. Am I correct, Professor? This in the middle position. Okay. So this the that first figure actually plot in a normal scale, and this one, the second one, a plot in a logarithmic scale. So explanation almost same. So the higher the stick means quicker relaxation time, and lower near the homo means near the homo relaxation less means their relaxation time is small. So I think so for that one, and this one and the first figure almost same. It's a high. It shows the higher relaxation. Sorry, quicker relaxation time. Higher the peak, that means higher stick, quicker relaxation time. It's relax so quickly. So this one, I think this one and the first figure is the most important figure for this plotting. So here, in this one is homo here, and this one and this uh, like I homo. It's actually it's a lumo. But so here it actually shows the transition between one orbital to another orbital. So if we um, photo excite from homo to lumo, it will relax from lumo back to homo. Actually, it shows how quickly transition return back to the ground state. Actually, it's how quickly relax the system and go back to the ground state. This one and this one, the last figure, actually in the y-axis it's the correlation function, and in the x-axis time. So here we able to see the like green dot dot and the red dot dot line. It goes to the uh, um, around 10 into 10 to the power 19, 10 to the power 3. It's goes straight. It happened because of uh, from my understanding that it happens because of that higher stick. So that higher stick shows that it's quickly relax the system and go back to the ground state. So that's why it goes to that way, like quickly goes to up. And after that, it's at the zero. There are lots of fluctuation, and when time increases, like 400, uh, more than 350. Suppose this one consider 375. From 375 to 500, their autocorrelation function almost zero. So that means the relaxation time, relax relax the system, we need more time. That's why it's like a plain zero. I think so. That's
okay. Okay, please join me thanking here.
Okay.
And paper is open for discussion and questions or constructive criticism or expression of admiration.
I have a question.
Please.
Your
Yes.
Kia, feel free to answer or
Of
help.
course.
How many orbitals should we select near the band gap?
Near the band gap?
Yeah, for instance, you mentioned you choose 80 orbital, for instance. So how many orbital is enough, for instance, 120, 50?
That one I said it's like example for like 4.
Yeah, I know. Maybe I don't know, Dr. Kirin or Gula, David can suggest. So because, for instance, for previous model PCBM, I chose just 20 orbital. So is it enough or no? We should do the calculation for a larger range of the orbitals.
I think it's better to if we choose the larger range. And now Professor can explain if I'm wrong. What I understand that we need to choose the larger range, not the smaller one.
Thank you, Keya, and thank you, Amir, for the question. So, the processes that we are trying to describe here typically deal with optical excitations, which are within 3 electron volts energy range. So, there is no reason to take into account states with energies that are more than 3 electron volts below HOMO or more than 3 electron volts higher than LUMO. So you basically look at energies, count 3 electron volts down, 3 electron volts up, and take only those orbitals. If you add other orbitals, it will not change your result, but it will change time you spend for calculations. If you're interested only in non-radiative recombination between LUMO and HOMO, you can include only 2 orbitals and do this calculation. But then it will be a little silly to do so complicated thing just for one number, because one can get additional things. And the larger number of orbitals will be important to those of us who is focusing on charge transfer, because some orbitals are localized in one part of the model, another away in the space, and as the population migrates between different orbitals, at the same time charge density migrates in space, and larger number of orbitals is needed for charge transfer in bigger extent than for photoluminescence. Is it enough, or maybe anyone in the audience have additional comments? Okay, more questions to Keya, or criticism or constructive suggestions.